Thank you for being here. Sorry for taking you away from lunch at this point. I hope you're all awake and attentive at this point. And I do hope this presentation acts like a small dessert for you. So this presentation is about the story of the Wayland driver for Wine and some of the challenges we have faced and are still facing. All right, so I assume that most people in this audience at least know what Wayland is and what Wine is, but perhaps some of you may not know exactly what the Wine driver is. So a Wine driver is the component that helps Wine integrate with the native Windows system. It does the mapping between the two worlds of Win32 and whatever the native system is in terms of input, output, window management, events. And Wine X11 is at the top because it's the oldest and most mature, and it enables Wine to integrate with an X server that's either a traditional X server, as we have known it for years and years, or these days with X.Wayland, which then can talk to a Wayland compositor. And this presentation is about a new driver that allows Wine to directly interact with the Wayland compositor without needing X11 in between, X.Wayland in between. So one thing I think that is clear at this point is that the first path, the traditional Wine X11 to X server, is becoming less and less relevant as time goes by. And I don't think it's going to be an important consideration like in the long term. But of course, we still have X.Wayland, and so we do have at this point a path from Wine to the Wayland compositor. And of course, the question is, why do we even want a Wayland driver since we already have some kind of solution? So, like the big picture here is that the fundamental vision is that we want to move towards a future that doesn't include X11. X11 had a good run, but it was designed for a different world. It makes different assumptions about how applications should behave and also is built on different security considerations. So at this point in time, I think for many people, Wine may be one of the few remaining pieces on their system that requires X11, even in the form of X.Wayland. And it's not inconceivable that going forward, at some point, X11 will effectively become like some kind of de facto Wayland protocol for Wine. And I mean, it's a really heavyweight protocol. I mean, probably we can do better than that. Okay, so that's the big picture. What about some more concrete concerns we have about X.Wayland? So first of all, X.Wayland requires integration with a compositor, and that has both an initial cost, but perhaps more importantly, it does have an ongoing complexity and maintenance cost. And that's maintenance both in terms of code, but also in terms of ensuring that X.Wayland and all that it requires, like in terms of window management, continues to play well with all the features and the policies that the compositor may want to have. So furthermore, the path through X.Wayland requires a double API translation, so from Win32 to X11 and then X11 to Wayland, which although may be good enough, like each step on its own may be good enough, it's still not lossless. So we do have the problem of introducing more bugs or more mismatches along the way. Also, X.Wayland is another layer in our stack, and all kinds of information, events, buffers flow through that. And as with most layers, it's not unreasonable to assume that at some point that it adds some overhead and affects performance, latency, etc. So we would like to remove that layer from our stack. And last but not least, since Wayland, I think everyone, at least here, agrees is the future and actually the present of display systems on Linux and other Unix systems possibly, it's where all the interesting new features and innovations will happen. So it's unlikely that X11 will receive counterparts to many of these innovations. And a good example of this is probably color management and HDR, which is being developed in a very full form and very capable form at this point for Wayland. All right, so hopefully everyone has been convinced now that we need a Wayland driver. But yeah, so how did the journey begin? So with all that in mind and with that lofty goal, a couple of years ago, we started on this journey to explore the viability of such a driver. So remember, this was, and still is to a degree, uncharted territory, and we weren't sure if there even was a treasure at the end. In fact, it was possibly worse than that, because it was uncharted land that we knew had dragons and krakens and all kind of monsters. So the primary goal of the first experimental phase was to convince ourselves first, and eventually the community, that this driver had potential. And this could not be achieved as like a pure thought exercise. So we needed to actually implement all the features that seemed kind of tricky or even potentially could be absolute blockers for the driver. And that's how our journey started. And I would like to share with you some of the challenges we have encountered along the way. So before, in the previous slides, I mentioned that Wine drivers need to take care of multiple aspects of the integration with the native system. But at the core of all those aspects is the event handling, and this is the first topic I'm going to present. All right, so time for a quick refresher of the Wayland event model on the client side. So Wayland clients create connections to the compositor, so that's through a socket. And through that, they can issue requests or receive events. So on the event side of things, so the incoming direction, there are two steps. First of all, we read from the socket. We get event data. We deserialize that. We figure out which Wayland object is the target to that event. And then we queue that. So that's the read prime there. We can create multiple event queues, and each Wayland object may be associated with a different event queue. So the second step is the dispatching of events, which for Wayland refers to calling the function the user has set to handle that event for that particular object. So we do that with function callbacks. And as long as we're careful and don't step off the well-trodden path, at least not too much, things tend to work nicely, even in the multi-threaded case. There are still pitfalls, especially with multi-threading, but that's what we have, and it's quite usable at the moment. Now for a quick overview of the Win32 message model. So events are messages in the Win32 world. So each thread that needs to interact with the user interface gets a message queue. And windows created by that thread get assigned to that message queue. Now, each thread is running its own like small message loop, and it dispatches events. So it reads from the message queue and sends them to the windows. Dispatching in Win32 is a bit different than Wayland because we don't have a callback mechanism. We have a single function, the window procedure, which receives the message type and some arguments, and basically then we have a huge switch statement that handles the message. All right, so that's how Win32 does things, but how does Wine integrate that message loop with the driver? And that's done by the process event callback function. So the idea is that each time the application would block waiting for a particular message type, so that means that there's no such message in the queue, Wine will ask the driver if it has any new messages of the type. It calls that process event function, and now if the driver has new events, it places them in the message queue. If not, the application returns back like a positive reply back to Wine. If not, the application then may sleep until something wakes it. This all depends on the particular Win32 API function that was called. So that's something that could wake up the thread. Is the driver itself informing Wine that it has new events that need to be processed and that could be interested in. And so for Wine X11, that mechanism that wakes up the thread is basically the connection FD. So Wine X11 gives the connection to the X server, the FD of the connection back to Wine. And when that becomes readable, Wine knows that perhaps there are new events and it wakes things up. All right, so that's the two models. And well, how can we integrate them for Wine Wayland? So as a first attempt, let's follow what all the other drivers are doing and follow this process event design. And in this case, each thread that has a message queue also gets a WL event queue. And we ensure that all Wayland objects created by that thread are assigned to that queue. Now, when the driver calls back to us, we just dispatch the thread and handle events, and that's done. Simple, right? But wait, what about that mask argument, so the type of events that we need to care about? Because in Wayland, we have no way to filter the events that we receive. So we have no choice but to bats them all. And then, in the end, things work out because we can mark if any of the match or any of the events that were dispatched match the masks, and then we can inform wine core with the right reply. So we don't react to the process events callback exactly how other drivers are doing it, but it's good enough. So what about sleeping and waking up? X11, wine X11 gave wine that FD to the connection, so perhaps we can do the same, but how many of these do we have? Well, wine X11 creates a different connection for each thread that needs some kind of user interface interaction. We cannot do that in Wayland. Well, I mean, we could do that, but this won't work because then objects that are created from different connections cannot be combined or referred to each other. And we might need that because, for example, we have a window in one thread, a window in another thread, and want to make them like a subsurface of the other. So yeah, all in all, it's workable, perhaps not great, but another benefit we get with this approach is that all events that have to do either with windows and surfaces on both sides, both on the Win32 and Wayland side, happen in the same thread. So we need to care less about synchronization, and the ordering is better handled in this case. But what about input? So Wayland is somewhat special in that input events are not events on surfaces, but rather events on a dedicated input object that is somewhat like roaming, transiently associated with surfaces. So in this picture, that poor mouse has no idea which queue it should be dispatched from. We can't select like one particular event queue because we don't know what the thread is doing if it even has like a proper main loop. So one idea would be, well, perhaps the ideal situation would be to kind of translate that to a per surface event kind of situation. And so the input events would be dispatched from the thread that has the window that has the focus for this particular input device. That would be probably doable, but it seems kind of tricky. There are ways to switch, like during runtime, to switch the queues objects are assigned to, but perhaps we can do better. One other idea would be to instead have all GUI threads handle input events. So yeah, many mice here, and we just react only to the events that are related to each thread. So all handlers are called, but some of them just return because they realize that, it's not their job to do anything at this point. Again, perhaps not ideal, but and of course rodent infestations are never good, but it's workable. But wait, what about outputs? So it's the similar story again, but we do have another consideration here, and the fact is that there are window API calls that need monitor information, which we can only give through WL output, that do not require the user interface, that don't require integration with the user interface. That means that that thread may not have a message queue, an event queue, may not have nothing. So, but fear not, because we all know that there is no problem in software engineering that cannot be solved by adding more threads, and that's exactly what we do now. So we have a new thread that processes WL outputs events. So how does that seem to you? Like the whole thing? Yeah? Good? Yeah. I mean, we started with this neat abstraction that kind of matched what other drivers were doing, but in the end, we ended up with mice all over threads. It's a bit complex. But one thing that we have established is that we need probably a different thread for at least the outputs. And let's explore more about this, and let's say, okay, what if all events are dispatched from one single thread? So how would I evaluate this? It's certainly simpler overall. A benefit of this is that we don't need to go through the process event mechanism at all, because we can just put events in the message queue, and that is enough to wake up threads, so we don't even need to register if these with wine core to wake us up. It provides a total order of all the Wayland events, and because all events are happening in the same thread, we need less locking for that. But on the other hand, we need more locking because now multiple threads may interact with like the surface, like the backing surface structures that we have. There are some other issues. Ask me more if you want to know more about this. But okay, so enough about event integration. And by the way, the previous approach was what we had in the experimental branch for a while. It served us well, but this is what we have in upstream, and I think it's much better actually. All right, so what about outputs now and output handling? So outputs are, or rather, I guess, monitors in the Win32 world are arranged in a virtual screen space, which is based on physical pixel units. All applications have access to this arrangement and can and do use it to make decisions about their own placement, like notably about becoming full screen. Okay, so that's what Win32 has. Let's see what Wayland has. Wayland core at least has absolutely nothing. For all we know, outputs could be arranged in a 4-dimensional space near a black hole, and that would be fine. We do get information about the mode of an output, so it's like a physical size in pixels. So at least we can use that to get the correct sizes and create monitors of the correct size. And potentially we could then do some arbitrary arrangement like side by side. And it would be probably workable for many cases. All right, so actually we can do a bit better because we have the XDG output protocol, which many people don't want, but we do have it, and it does provide us with some interesting positioning information in what it calls a logical compositor space. So in many cases, that logical space will match the physical pixel space, so we can use that information directly and know it's fine and good. But often, in the case of scaled outputs, for example, the logical and physical pixel spaces don't match, so what to do? One option is to just use the logical space for everything, and that actually could work for many applications. It's fine. Unfortunately, doing this prevents Win32 applications from using the full resolution of the monitor, because as I said before, applications have access to that arrangement and size and monitors, and they do use that to make decisions about their own sizes, for example. So the alternative is to stick with physical pixel sizes, but try to replicate the arrangement from the logical size in the monitors, like the virtual screen space. And this does provide the full resolution, and the trade-off there is that mapping from like logical space to virtual screen space, if we like blow up things that are scaled up, then there's no really correct way to do that. But we do have an algorithm that has great, I would say, excellent results, at least for like not super exotic cases of placements. So it should be enough for probably the majority of the users. Related to outputs, we have display mode changes. So Win32 allows arbitrary applications to change the hardware display mode, and this is mostly useful for full screen games, of course, at this point. And although Wayland doesn't support this for good reasons, it does provide excellent facilities to emulate this. In particular, it allows clients to request that the compositor scales their surfaces to a particular other size. We do that with a WP viewporter protocol. So here, how it would work, and how it does work in the experimental driver, because we haven't yet implemented that upstream. So first of all, we expose a variety of common modes that applications may want to use that can fit into our like native Wayland mode. When an app requests a mode change, we just accept it. Everything is fine from the application perspective. Everything is changed. The virtual screen arrangement is changed also. And when it is time to present on screen, we use the WP viewport to scale up the application, the surface of the application. And this is particularly nice because it's completely transparent to most of the other driver code. The exception is that we now have multiple coordinate spaces, and we need to take care of that to ensure that we're handling things in a proper coordinate space. But other than that, it works great. And another good thing is that in the full screen case in particular, Wayland, the Wayland compositor will place the bars around correctly, so everything is really very easy. All right, so that's enough about display. And I now welcome you to the Twilight Zone because I'm going to talk about window management. So at the core of this, of the difference between the two systems, we have a fundamental disagreement about how window management works. So Win32 follows like the 80s, 90s approach of being prescriptive. So applications tell the system exactly, and in an excruciating detail most of the time, what to do with a window. In most cases, the system does accept what the application tells it to do. On the other hand, we have Wayland, which follows the more modern and descriptive approach. So applications tend to tell the system what the Windows, for example, state is, or rather what they want it to be. And then the compositor makes decisions based on that. So an implication of this prescriptive versus descriptive difference is a matter of control. So in Win32, applications have almost full control. In the Wayland world, the compositor has more control, and the idea is that the user then, through the compositor, has more control. So again, a primary example of the differences between the two systems is full screening, which is completely different in the two systems. So in Win32, the application query the outputs, position themselves to cover a particular output, and that's full screen. In the Wayland case, applications request the full screen state from the compositor, possibly on some particular output. But then the compositor is free to deny that request. And yeah, tough luck if you're an application. So let's see now some more concrete examples of how we handle window management. And let's start with top-level windows. So top-level windows in this context are windows that perhaps may have some kind of decorations, but the main point here is that they are controllable by the user in terms of position, size, and this is a natural map for the XDG top level, and indeed that's the Wayland object or abstraction we are using to back Win32 top level windows. So when Wine tells us that it's time to interactively move or resize a window, we just feed that request directly to the compositor. And in the resize case, the compositor may react with a series of configure events. And in the move case, it doesn't do anything, because we don't have a global coordinate system, we can't request a particular position and also cannot access our position. And that, of course, creates problems. A big part of window management is, for top-level windows, is state and size synchronization. So the two systems have their own idea about what the state and the size is, and we need to synchronize. Changes may come from either direction, and we need to handle that. So I mentioned just before that we can't actually access our position in terms of where a window is in the Wayland world, but we can get a very coarse position synchronization idea, and that's implemented only in the experimental branch. Because we do have surface leave and enter events from particular outputs, and what we can do is track those and kind of warp the windows in the Win32 side in the origin, at the origin of the windows that we think that the window is actually in. So yeah, that may sound a bit hacky, and it is, but it tends to produce reasonable results for applications. All right, so here is an example of window management that is initiated by Wine. So Wine asks us to maximize. That ends up in the driver, in a driver callback that tells us that to change our position, perhaps in size along with state. At that point, we check the window state and the backing surface state, and we realize that, oh, okay, so there's a difference. And then we request the maximized state from the compositor. The compositor eventually replies with a configure event. That configure event could be a denial of our request, but it doesn't matter. Then we call back into Wine again using high-level APIs to update the size and the state based on what the compositor has told us. And that's especially needed in this case because set maximized has very strict size constraints. And then finally, Wine gives us back like and some notification that okay, this is a new state, and we apply that. And at that point, we figure out, there's no difference, for example, so we don't get into infinite loops. Don't worry. And then we have a compositor initiated change. That's simpler. The main reason it's simpler is because basically Wine cannot really deny a request, so we don't have a negotiation phase. So the compositor tells us we're maximized. We update, we tell Wine core that we need to update the size and the state, and it gives us back the final size and state, and we basically apply that. And that's, window management mostly. But before we move on from top-level windows, I would like to mention one of the problems caused by the lack of position synchronization due to the lack of absolute positioning. So let's say that we have an application and a surface on the Wayland side of things. It's completely visible, but for whatever reason, it's not completely visible, like within the virtual screen space of Win32. If a user clicks at the point in the window that's outside the screen space, Wine will clip it to the edges of the virtual screen space. And that will lead to a very confused and probably angry user. It really is very annoying. We don't have a really good solution for this at this time. We have been discussing with Upstream about things to do. So that coarse position synchronization that I mentioned before of putting windows at the origin kind of helps because it ensures that windows have, they're likely not outside the virtual screen space and can take advantage of the whole screen space. But yeah, that's kind of a hack. All right, so next up we have transient windows, and by that I mean pop-ups, tooltips, menus, and in general, windows that the application has more control over in terms of the position and size rather than the user. And many of these are conceptually positioned relatively to some other window, let's say the parent window, although that term is a bit overloaded in Win32. So, of course, the natural mapping is WL subsurface. We're not using, for example, XDG pop-up and other more heavy abstractions because those kind of lead to some behavior on the compositor side that we may not want. So, yeah, the problem is then that on the Win32 side, the position of such windows typically, even they may be conceptually relative, is expressed in absolute terms. And we also do not get enough information about who their parent may be. And even worse, we typically don't get direct information about their transient nature. There's nothing to tell us that this is a pop-up. So in order to overcome these obstacles, we resort to heuristics. So for example, we might say, well, a window that is on top, that's set to be on top all the time. It's relatively small. It doesn't have like top bar elements and captions and stuff like that. That could be like a transient window. And again, who is the parent of that window? We can guess based on heuristics, for example, like the overlap, the activation state of some other window, or perhaps which window was the target of the last input. And I must say that relatively simple heuristics like this have worked really, really well in the experimental branch. But of course, any attempt to map between the two worlds in terms of like incomplete information like this is inherently imperfect. So there are some concern about using those heuristics in Upstream. But at the same time, one thing is clear that at least with the current collections of Wayland protocols, we don't have any other viable choices. So that's that. Now, for going to input, So input is relatively straightforward, except for the issue with the virtual screen I mentioned before. We translate from surface local to virtual screen coordinates. We send events like as hardware events to Wine. We can handle cursors that we can fill with bitmap data or from a Wayland theme, if that's available. A problem here, though, is how to deal with applications that set the cursor position. And this is not something that's inherently supported by Wayland. But, well, in reality, warping the cursor around on screen is not typically very useful, except in very particular scenarios, even for Win32 applications. And that scenario that it's mostly useful for is relative motion. And here is how it works. So the app constrains the cursor to a particular area within its usually client area, and then centers the cursor to the middle of that area. So then as the cursor moves, it receives events in absolute terms, but because it knows what the beginning position was, it can infer relative information for that. And then it moves back, uses set cursor position to move back the cursor to the center, for example. So the trick here is to realize that the only reason the pointers warp back to the beginning is to allow enough space around the cursor for movement in order to be able to get that absolute and then relative information. But happily in Wayland, we do have a protocol to provide these relative position changes, and we can also constrain the cursor. So it's just a matter of detecting when to switch to this relative motion mode. And again, we can use heuristics like cursor visibility, like clipping, whether the application is using, in fact, set some position to force the cursor to a position, to a particular point in the window. And perhaps simpler would be to use relative motion all the time, and that's enticing. I have tried to do that, but I have seen some drift. Perhaps I was doing something wrong. But if that works, it's even better because then we won't need the heuristics. And yeah, that's for the mouse. And now for keyboard, well, this is the shortest slide because basic operation is generally straightforward. The major complication is that we need to map key maps from XKB key maps to Win32 keyboard configurations. So then we'll be able to emit the correct scan codes and virtual codes that applications expect. So in the experimental driver, we copied effectively what Wine X11 was doing, some like algorithmic matches between key maps and keyboard configurations. But luckily, Upstream is experimenting with a simpler solution. Remy Bernon actually recently from Wine Upstream is working on that, so perhaps we can avoid that. Nice, so yeah, input, we're done with input, and now to GL and Vulkan. So the driver's goal for GL and Vulkan is basically to translate between WSIs. So for example, we translate between WGL and EGL in our case, and between Vulkan Win32 WSI and Vulkan Wayland WSI. One complication here is that under Win32, when WGL, for example, and Vulkan target a window, they target its client area, and everything that's rendered then appears there. In Wayland, because we deal with full buffers, we can actually we can't actually do that. So our solution is to use a subsurface over the client area for GL Vulkan content. We'll make it desync, so we can keep drawing on that, and everything is fine. So GL front buffer rendering is another issue. It's used in a special way. I won't go into details because I apparently have exceeded my time, but ask me later. But yeah, things are generally fine and straightforward. Except for the matter of cross-process rendering. So under Windows, it's a free-for-all situation. Like processes can render into the client areas of other windows. And this wouldn't be too much of a problem, except Chromium does this, and then Chromium Embedded Framework applications do this, and it turns out a lot of like game stores and launchers, for example, use this, so it would be nice to support that. That's, yeah, kind of tricky to implement. Wayland actually makes this easier than other systems because we do have separate buffers and buffer objects we can pass around. And this is how it works, again, if you want more information. So in the experimental branch, we have a protocol based on message, window messages to do this. So ask me more if you want more information. All right, so this were some of the challenges. We're now in the past the experimental phase. We have started upstreaming, and I considered the experimental phase a success in the sense that it showed us that there's a viable path forward. We are now continuing with the upstreaming with a goal to build a Wayland driver on solid foundations so it can have a long and fruitful future. And closing, I would first like to thank contributors to the experimental branch, particularly my colleagues, Leandro Ribeiro and Sergio Andres Gomez de Real, for their great work, the many brave people that tested this in the community, and also the wider community for embracing this with excitement. I would like to thank Wine Upstream, first of all for Wine, which is a fantastic and tremendous feat of engineering. Especially, I would like to thank Remy Bernon, who has been my main reviewer for the upstreaming work and has been providing excellent guidance and insights. And last but not least, I would like to thank Google for supporting this work and helping the whole ecosystem move forwards towards a Wayland-only future. And that's it. Questions? I'm happy that everything was so clear. Oh no, something wasn't clear.
I'm curious to know, since this is still very much work in progress, can you tell yet, or do you have an estimate, if this is going to be a fully viable alternative to running the X11 driver on X.Wayland? Or will there be use cases where Wayland might be too limiting to actually support applications properly?
Right, so I would say the second. So there are unless we come up with some new protocols, there will be cases where X.Wayland would be the way to go. But the experimental branch has shown me, and possibly, hopefully, the whole community, that these cases are actually fewer than we may have thought before. And I mean, if you have an application that does very exotic window management and stuff, then perhaps it won't work properly with Wayland. But still, I mean, I was able to get LibreOffice working, GIMP, like Win32 working, so I guess, yeah, who knows?
Yeah, hi. Thank you a lot for working on this. Have you looked into like drag and drop and clipboard in general, or not yet?
Sorry, the drag and drop?
Drag and drop and clipboard, like selection, clipboard?
Yeah, so the experimental branch does support copy-paste in both directions. I didn't mention that here. And drag and drop in one direction. I don't remember which direction now, but only in one, probably from Wayland into Wine.
Yeah. Do you need to resort to hacks to kind of figure out what the drag icon looks like and stuff like this, or is it mostly straightforward?
Well, it was relatively straightforward, but again, in the context of the experimental branch, perhaps when it's the time to upstream, something would come up I haven't thought about.
Nice.
And by the way, most of the things I've mentioned about, I have published a series of YouTube videos. You can watch many of them, and all of those features are in. So you can see them in action.
What about window decorations? Are they provided?
Okay, so window decorations at this point, you'll have like the pure Win95 experience when you run the driver. That's retro stuff. So there have been some thoughts about, for example, using libdecor, but it doesn't really match how the driver works and needs to integrate with Wine. So I don't see that coming anytime soon. I think the next possible step is to be able to enable compositor side decorations. That could probably be one thing we could do.
Thanks.
Hi. So as far as I know, there's no guarantee that the compositor will actually draw all of a subsurface if it is overlapping with the main, extending beyond the main area of the original window, which is usually not an issue in floating window managers, which will do that happily, but with tiling window managers. Is this something that is taken into consideration when choosing via the heuristics if this is another top-level window or transient window, or not at all?
Yeah, no, I'm not taking that in experimental version into consideration. So you mean we have a top-level window and be a bit on the side or outside? Yeah, that's not taken into consideration. But the thing is, by using double subsurface, we are letting the Wine side of things position things, let's say. And if things match more or less, if the positions match more or less, it will be visible at least, not ideally, but
yeah, I'm just concerned about submenus going off the window or something like that.
Yeah,
so
yeah,
that's the one reason why XDG pop-up might be very nice, as long as you can deal with all the constraint stuff, because that would probably be drawn correctly.
Yeah, and certainly this could be worth exploring. That for some windows that we think XDG pop-up would be a good match, could use that. It would be not too complicated, I think, to give it that role instead of subsurface.
Thanks.
All right, so no more questions, I think. So thank you very much again for attending this talk.